Hello, my name's Kason Markley with the University of Illinois at Springfield, and today we're going to be talking about how to use proton nuclear magnetic resonance, or NMR, as well as carbon-13 NMR to determine the structure from a given formula. So, first thing you need to know is that nuclear magnetic resonance measures the chemical shift of protons in proton NMR. And so what that means is that protons have their own magnetic field, which causes them to spin. This is known as their alpha state. When you place these in an induced magnetic field, that can cause their spin state to flip into their beta state. Now, when you add those fields together, you get what's called the effective magnetic field, and that is what's going to raise from your alpha state to your beta state. And then what proton NMR actually measures is the difference between the states, also known as the chemical shift. Another thing you need to know is the hydrogen deficiency index. Now, if you remember from MS and IR spectroscopy, this is very similar to the degrees of unsaturation. However, this strictly focuses just on the number of hydrogens missing. You don't need to worry about halides or anything else like that. And so, in order to find the max number of hydrogens, you need to multiply your number of carbons plus 2. And then to find your HDI, you need to take that number minus the number of hydrogens you currently have in your molecule and divide that by 2. Now you should get an integer for this, and for every deficiency, that corresponds to either a pi bond or a ring structure in your molecule. And finally, you need to know about integration values. Now you're going to use these to find relative ratios of protons giving off a signal. Now these are going to be your small numbers there underneath the peaks. What you're going to do is you're going to divide all these values by the smallest number. And then once you get those numbers, you'll approximate those to a simple fraction to keep it easy. But you obviously can't have a partial proton, so you need to multiply those all to get integers. Next, you have your environments. Now, environments refer to chemicals, how the protons reacting chemically. So every proton can be chemically unique in terms of how it's placed around your molecule, and if it was, this would produce a different chemical shift for each proton. But since many protons can be placed in very similar places, this can produce protons that are chemically equivalent. This means that they're in the same environment and that they're all going to produce one signal, but it's going to be wider and much stronger. Now, neighboring protons, however, can kind of distort this field, because remember, protons not only produce their own field, but they can be influenced by outside fields. And so if they're nearby, they can split your peaks, and this is called spin-spin coupling. Now, what that's going to tell you, the number of peaks minus 1, or N-1 rule, is going to tell you how many hydrogens are nearby or neighboring your environment group. Not neighboring each other, just how many are neighboring that entire environment. Now, electrons actually shield the protons. This helps reduce your effective magnetic field, but if you have a very electronegative atom, such as an oxygen, it can de-shield those protons by drawing that electron density away. And so as that density is moved, the shielding goes down, and because that went down, that's going to increase your effective magnetic field. And so you're going to get a stronger signal. Now, each functional group that you're going to see is going to have its own unique chemical shift ranges. Now, a lot of different groups are going to be found in the same ranges, but as you can see, some are found in very wide ranges, some are found in very narrow ranges. Now, when you're looking at a graphic like this from Compound Chem, what you see on the bottom is marked in parts per million, and that's your chemical shift. As you go higher on the scale, you're going to see some higher values, and this is going to be called your downfield. And then as you go towards your lower values, this is called your upfield, which is a little counterintuitive, but it's how it is. Now, the steps for finding out your structures through your proton NMR. So you'll have your given formula, and so in this case we're going to use C6H10O. Then you're going to calculate your hydrogen deficiency index, followed by determining your number of environments. Then you're going to figure out your integration values. You're going to use your N-1 rule to find the number of neighboring protons. And then finally, you're going to match the chemical shift signals to some known ranges. So to start off with, we already have our formula. So we'll go ahead and move right on to the hydrogen deficiency index. And so you remember the equation from before, the 2C plus 2 minus the number of hydrogens in your molecule divided by 2. So we just plug in the number of hydrogens, or carbons, which was 6. When you do all that math, you'll end up with a hydrogen deficiency index of 2. And what this means is you either have 2 pi bonds, 2 ring structures, or one of each. So if we go on to our spectrum here, you'll see that we have 2 big peaks. This is our 2 chemical shifts. So this means we have 2 separate environments. Now if we look at our first environment, you'll see that we have 2 peaks. If we use our N-1 rule, it means that 2 minus 1 will have 1 neighbor. If we use that same rule for the second environment, you'll see that we have 2 neighbors because we have 3 peaks. 3 minus 1 is 2. Now if we look at our integration values, you'll see that the smallest number, which is circled, is 325. And so like I said, you have to divide all the values you see by the smallest. And so when you do that, 325 divided by itself is obviously 1. But 498 divided by 325 is close to about 1.5. Now you can't have half a proton, so you have to multiply these by 2 to make them all integers. And so 1 times 2 is 2, 1.5 times 2 will give you 3. Now this would say that we have 5 hydrogens in our molecule, but we know that we have 10. And so we need to change our ratio from 2 to 3 to accommodate for the total number of hydrogens. And if we multiply that by 2, we'll get a ratio of 4 to 6, which equals our 10 total hydrogens. And as you can see there, our first group is going to have 4, with the second group having 6. Now this just shows a couple of zoomed in spots for our functional groups, just to make them a little easier to see. So we put in our second environment, which was at about 1.8 parts per million. Then we have our second group, which was at about 2.4 parts per million. You'll see that the first group passes through the alcohols, the allylics, and the alkyl groups, while our second passes through the alcohols as well, our ketones and our benzylics. So I know that was a whole lot of information, so let's try and put it all together. So in environment 1, we saw that we had 2 peaks, and using our N-1 rule, that means we had 1 neighbor. Our chemical shift was about 2.4, and because of that, some of our possible functional groups were alcohols, benzylic derivatives, or ketones. And we know that because of our integration values that this should encompass 4 hydrogens. Now in our second environment, we have 3 peaks, which using N-1 gives us 2 neighbors. We have a chemical shift of about 1.8. Because of that, our possible functional groups are our alkyls, allylics, or alcohols. And then our integration values again gave us 6 hydrogens. And then finally, we just have our hydrogen deficiency index of 2. And so you're going to have to play around with this a little bit to see what might work, but it's generally going to give you a lot of little hints that'll help. Alright, so first we'll focus on the hydrogen deficiency index, because this will tell us where we have double bonds or rings. So environment 1 we know passes through the ketones range, and since we only have 1 oxygen present, it's pretty reasonable to assume that we'll have a carbonyl group, and since it's a ketone, it'll have 2 carbons attached to it as well. So I just went ahead and drew that in there. And so if we take those 3 carbons and our oxygen out, that reduces our formula to C3H10, which leaves us with 1 remaining hydrogen deficiency index. Now if we look at environment 2, we notice that we still have one of our deficiencies left. So I went ahead and put up the same graphic from earlier. Now we'd be tempted to think, okay, this is probably an allylic or another double bond. However, if you do that, it puts up a possible structure here. Now if you were to do that, you'll notice that this particular one creates 5 unique chemical signatures. And based on our integrations, we only have 2. So most likely what we need is something probably a little more uniform or symmetrical that's going to give all of our hydrogens the same environments. Now if you'll notice, even though our line does not pass directly through it, it is still pretty close to the alkyl groups. And so that, combined with the fact that we only have 6 carbons, suggests that we probably have a ring instead of a double bond. So if we go along those lines, since we have 6 carbons, it's probably good to put them all in one ring. And that's going to include our 3 ketone carbons, so that the ketone is going to be bonded directly onto our ring. Now, because of the carbonyl group, we can't have benzene. So right now what we have shown is the cycloalkanone. And this is very possible. Like I said, the ring structure eliminates our final HDI. It's composed of a lot of alkyl groups, which, again, not straight through our signal, but it's pretty close. Our total number of hydrogens add up, as well as our other atoms. And if you'll see here, our number of environments match. We have 2 green environments, and we have 3 red environments. And then you'll notice our number of neighbors also matches up. So for each green environment, it only has 1 red neighbor. But the whole red groups, which are all together, have 2 green neighbors next to them. So you'll see all that adds up very nicely. And so if this were true to be our structure, it would be called cyclohexanone. And so you'll wonder, is this what we have? And the answer is yes, the structure is cyclohexanone. And as you can see on the graphic there, it already labels different environments for us. But let's say you didn't automatically know what the structure was, and what would be a great way to check it would be to use carbon-13 NMR. Now, carbon-13 NMR is pretty similar to proton NMR, except for instead of using hydrogen protons, it uses carbon-13 isotopes, which take a lot less energy to induce the spin states in. But carbon-13s are a little bit different than protons in how you go about solving them. Carbon-13s have a lot more protons, neutrons, and electrons surrounding them, and so they're a lot better shielded than lone protons. And because of that, you're not going to see much spin-spin coupling. Now that's going to mess with a couple of your steps, because it means you're not going to be able to use your integration values to find the number of carbons, and it means your peaks are not going to split, so you don't know anything about neighboring. So how does that affect the steps? Well, first, you're still going to have a given formula. So our formula is going to stay the same, C6H10O. You're still going to calculate your hydrogen deficiency index. You still want to find the number of environments. However, now, instead of looking for proton environments, you're looking for carbon environments. And 4, you want to match your chemical signals to known ranges, just like before. So we have our formula there. Now, if you look, you'll see 4 distinct peaks. And we also have a hydrogen deficiency index of 2. So those 4 peaks are going to tell us that we have 4 unique environments. Now the first one has a chemical shift of about 215 parts per million. The second one at about 42, and third at 27, and then fourth at 26. Now you notice that the fourth at 26 is very similar to our 27, but they're not exactly the same. Now the fact that they're this close means they're likely the same group, but their placement may be a little different. So here we have just another guide from Compound Chem, and you notice this little tidbit of information down here in the lower left that shows you that carbon-13s are very rare compared to carbon-12s, and that's what makes them so useful for carbon-13 NMR. Also, carbon-12s do not have a spin state unlike the 13s, and so these two together means that the signals are unlikely to interfere with each other, and so we get a very nice clean reading. And then similar to the proton NMR, you'll see a lot of different groups have very wide ranges and then some have very narrow ranges. The only difference is the value for their chemical shifts as well as how far some of the shifts are. So if we look specifically at our chemical shifts, we have some segments here that I spliced together to make them a lot easier to read. So we have our 4 different groups. So we're going to look at each one individually just to make it a little easier. So in environment 1, which if you recall happened at about 215 parts per million, and show you a little snippet there. Notice that it is well within our ketone group. And so it's pretty likely that that's what that particular signal is. And so if you'll remember from the proton NMR, That's going to steal away 1 oxygen and 3 carbons, and so it's going to reduce our chemical formula down to C3H10. And since ketones have a carbonyl group, they're going to use one of our deficiencies. And I'm just drawing in the structure there. You see it's the same as in the proton NMR. Now in environment 2, which happened at a much lower chemical shift of about 42 parts per million, you'll see that this spectrum shows it to be in our alkyl range. Now this is primary, tertiary, and secondary, as well as our alkyl halides. Now obviously it can't be an alkyl halide because our formula doesn't contain any halides, but it's still likely that it's a primary or tertiary alkyl. Now you'll notice that this signal is much stronger than the first one, and so it's quite likely that we have more than 1 carbon in this particular environment. Now in environment 3, which occurs a little lower at 27 parts per million, this is also still in our alkyl range. Now again, it can't be an alkyl halide, but it could be primary, secondary, or a tertiary alkyl. Now the fact that we keep getting more alkyl groups suggests that we're either going to have a large chain or we're likely to have a ring. And again, this has a much stronger signal than the first one, and so it's likely that we have more than 1 carbon in this environment. Then finally in environment 4, which was only just a little bit lower at 26, you'll see that it's almost identical to environment number 3, but its chemical shift is still slightly lower. Now what this is going to tell you is that it's probably just that little bit further from an electronegative atom. The reason for this is, if you recall earlier, I mentioned that electronegative atoms draw away electron density, and that de-shields the protons. Well, it does the same thing for carbon-13s. As it draws away those electron densities, carbons are less shielded, and so they experience more of that magnetic field, and that's going to lower their chemical shift. Now, if you remember, we still only have 1 hydrogen deficiency index left. Now we need to know, is it a ring or a pi bond? So if it's a pi bond, it's probably going to form some tertiary alkyls. So I'm going to use the same example structure from earlier. Now if it's a ring, we're going to see a lot of secondary alkyls. That's the same one from earlier as well. But which one really is it? Well, let's assume it's a pi bond. And so we'll bring the structure again here. And so if we look at this, we'll see that we have the correct number of atoms, and the fact that we have 2 pi bonds brings our hydrogen deficiency index to 0. But circled, you'll see that we have the wrong number of environments. We have 6 potential carbon environments, and due to our spectra, we only have 4. And so this structure cannot be possible, at least not for the formula we were given. So instead, let's look and see what it would be if it was a ring. So we'll bring that structure back up. If you look again, we have the correct number of atoms. Instead of 2 pi bonds, we have 1 pi bond and a ring. So that's going to give us still a hydrogen deficiency index of 0. And now we have the correct number of environments. You'll see we have the 1 green environment, 2 light blue environments, 2 dark blue environments, and then 1 red. So you see we have 4 different colors, 4 different environments. And you'll see on the red environment that it demonstrates what I said earlier about the electronegative atom. You can see it looks very similar to the dark blue environments, but it is that little bit further away from the oxygen. So that's why it has a very similar signal, but not quite the same. And so if we compile all those results in, we look and see our hydrogen NMR, which gave us this structure, and our carbon-13 structure, which was the same structure. Put those together, and they both come out to the same structure. And so either way can be effective to finding your structure, but they're also really good at checking each other.